the spliceosome, some introns are capable of catalyzing the chemistry of their own release. These self-splicing introns are divided into two classes based on their mechanism of self-splicing: Group 1 introns and Group 2 introns. When you have completed this exercise, you should understand the structure of Group 1 introns, understand the mechanism of self-splicing by Group 1 introns, and understand how Group 1 introns use cyclization to prevent themselves from participating in the reverse reaction. The first Group 1 intron was identified in the ribosomal RNA of Tetrahymena thermophila, a unicellular, ciliated freshwater protozoan. In fact, this Group 1 intron was the first RNA molecule proven to be capable of catalyzing a chemical reaction without the aid of proteins. Such catalytic RNA molecules are called ribozymes. Group 1 introns are capable of folding back onto themselves, forming a complex secondary structure. This secondary structure can further fold into a tertiary structure. This tertiary structure contains two important features: a guanine binding pocket and an internal guide sequence. The internal guide sequence is capable of base pairing with the exon at the 5' end of the RNA molecule. The guanine binding pocket is capable of binding any guanine-containing ribonucleotide, including guanosine, GMP, GDP, GTP, or an RNA molecule that terminates in a guanine residue. To begin self-splicing, a free guanine-containing ribonucleotide binds in the guanine binding pocket. The 3' hydroxyl of this guanosine attacks the phosphate at the 5' end of the intron. This transesterification reaction fuses the guanosine to the 5' free end of the intron. The freed 3' hydroxyl of the exon then attacks a phosphate at the 5' end of the other exon. This fuses the two exons and releases the intron. The internal guide sequence is also capable of base pairing with a sequence near the 5' end of the excised intron. The intron also has a guanosine at the 3' terminus. This guanosine can bind in the guanine binding pocket. The 3' hydroxyl of the bound guanosine attacks a phosphate to the right of the internal guide sequence, using the same transesterification mechanism used to splice the exons. This reaction is called cyclization. The new bond between the 3' guanosine and a phosphate at the 5' end of the intron is easily hydrolyzed. However, since the intron has been cleaved, the intron is unable to fold properly and catalyze the reverse reaction to splice itself back between the exons. Group 1 introns have been widely studied for potential therapeutic and experimental uses. In this section, you will explore some of these possible uses. Question 1. Since Group 1 introns have a turnover number of 1, they are not technically enzymes. Which of the following would be necessary to convert a Group 1 intron into a true enzyme? Question 2. You wish to construct a ribozyme from a Group 1 intron which will cleave RNA at a specific sequence. What part of the intron could you modify to change its sequence specificity? Question 3. Given this target sequence, what does the internal guide sequence of the intron-derived ribozyme need to be? Question 4. Which of the following is a possible danger in this approach? Question 5. A cell contains an RNA molecule with a defective 3' sequence. How could you use a group 1 intron-derived ribozyme to repair this RNA molecule? Question 6. Which of the following is a drawback of the method used in question 5 to repair a defective RNA molecule? Group 1 introns are catalytic RNA molecules capable of splicing themselves out of an RNA transcript. Group 1 introns fold into complex secondary and tertiary structures. The tertiary structure contains two important features: a guanine binding pocket and an internal guide sequence. A free guanine-containing ribonucleotide binds in the guanine binding pocket, and the 3' hydroxyl of this guanosine attacks the phosphate at the 5' end of the intron. The freed 3' hydroxyl of the exon attacks a phosphate at the 5' end of the other exon, fusing the two exons and releasing the intron. The intron then undergoes cyclization. This reaction destroys the tertiary structure of the intron, preventing it from catalyzing the back reaction to reinsert itself into the RNA transcript. You have completed this exercise. While most introns are removed using a